Hi everybody. In this one-dimensional motion example, let's imagine that the position as a function of time for some object is given by x equals 9 meters per second times time minus 1/3 meters per second cubed times time cubed. Let's imagine that this is valid from time equals 0 until when the velocity first equals 0 according to this expression. So here are the questions we want to answer. First, we want to find the velocity and acceleration as a function of time. We want to know when the object first comes to rest. We want to calculate the average velocity from time equals 0 until when it comes to rest. And then we want to show also that the average velocity cannot be obtained by taking the initial velocity, the final velocity, adding them up and dividing by 2. And then finally, at the end, we want to interpret the signs of our answers, assuming that north is a positive x direction. All right, here we go. Before we solve these problems, let's first check the units on our position versus time expression. Position should have units of length, so each of these terms in the expression should have units of length. So in our first term, we've got length over time times time, so that comes out to length. In our second term in the expression, we got length over time cubed times time cubed. That's also going to come out to length as well. So our units are good for our position versus time expression. All right, so let's find the velocity as a function of time. Well, we could use the definition of the velocity, the derivative of the position with respect to time. We'll write that right here. So that means we need to take the derivative of this expression with respect to time. Taking the derivative of the first term, we've got a constant that comes through, and so we've got derivative of time with respect to time, which gives us 1. So our first term just is 9 meters per second, and that comes down here. Moving on to our second term, we have plus a negative 1/3 meters per second cubed. All of that's a constant now times time cubed. Derivative of t cubed with respect to t will be 3t squared. The 3 cancels the 1/3. We're going to be left with negative 1 meter per second cubed times t squared. That'll go right here. And this is our expression for the velocity as a function of time. Notice that at time 0, we'll start out with 9 meters per second, positive, and then as we put ever greater times in here, we'll be subtracting off an ever larger number from the 9 meters per second. All right, let's look at the acceleration as a function of time. The acceleration is just the derivative of the velocity with respect to time, so we can put that right here. So now we need to take the derivative of this expression with respect to time. Derivative with respect to time of 9 meters per second is 0 because this is a constant. Now with this term, our little constant slides out front. Derivative of t squared with respect to t gives me 2t, and so we're left with, before we move on, let's check the units in our expressions. Velocity should have units of length over time, so we've got length over time here. We've got length over time cubed times time squared, so that'll be length over time. Acceleration should be length over time squared. We've got length over time cubed times time, giving us the length over time squared, so the units check out. And we see that for all times, any time greater than 0, this acceleration will be negative. All right, let's move on to part B. At what time does the object come to rest? Well, we can look at our velocity versus time expression, set the velocity equal to 0, and solve for the time at which that happens. So I'll plug in 0 for this and rewrite this expression right here. I can add this term to both sides. Let me get all the units on one side by dividing both sides by meters and multiplying both sides by seconds cubed. If I do that, I'll get this. And if I take the square root of both sides, I'll get t equals plus or minus 3 seconds, which I'll write here. Now let's look at these answers. Our clock started at t equals 0, so negative 3 seconds is before the time period where we're talking about this motion. So the negative 3 seconds is non-physical. I can cross it out. And the positive 3 seconds gives us the first time after t equals 0 at which the velocity is 0. So now with this information, we can reinterpret the given. This expression for position as a function of time is valid from t equals 0 until t equals 3 seconds. And I'll just plug that in here. All right, so now let's find the average velocity from t equals 0 until when the velocity is 0, that is at time t equals 3 seconds. To do that, we use the definition of the average velocity, which is the change in position over change in time, so I'll put that here. The change in position is the change in position from t equals 0 to t equals 3 seconds, that is the position at 3 seconds minus the position at 0 seconds. And the change in time is just the change in time from t equals 0 seconds to t equals 3 seconds. So we'll have 3 seconds minus 0 seconds gives us 3 seconds. And I'll just put that in here. So now we need the position at 3 seconds and the position at 0 seconds. Let's do the position at 0 seconds first. So plugging in 0 for the time in our position versus time expression, we'll have this times 0 minus this times 0 cubed. All that will be 0. So the position at time 0 is just 0. So now let's get the position at time 3 seconds. To get the position at t equals 3 seconds, we'll plug in 3 seconds for each of these times. 9 meters per second times 3 seconds will give us 27 meters. Then I'll have minus 1/3. And this time will be cubed, so I'll have 3 seconds cubed. That'll give me 27 seconds cubed. The seconds cubed divided by seconds cubed will cancel, and then 27 divided by 3 is 9. So I'll be left with minus 9 meters. And then this will give me 18 meters. So our change in position will be 18 meters minus 0 meters, or 18 meters. So we can rewrite that and put that in for the denominator. Our denominator is still 3 seconds. So I'll have 18 meters divided by 3 seconds, or 6 meters per second. And that will be our average velocity for the time interval t equals 0 till when the velocity is 0, which is at t equals 3 seconds. All right, for the next part, I want to show that this average velocity that we just calculated is not equal to the sum of the initial and final velocities divided by 2. So to do that, let's find the initial velocity. That is the velocity at t equals 0, which I can write right here. So to get that, we can plug t equals 0 into our velocity versus time expression. This term becomes 0, and we're left with 9 meters per second for the velocity at time 0. The velocity at time 3 seconds, all we've got to do is plug in 3 seconds for the time here. We'll have 9 meters per second minus 1 times 3 seconds squared. And so we're going to get 0 meters per second, which of course it had to be because we assumed that we were taking this equation to be valid until when the velocity first became 0. That was at t equals 3 seconds. So that was just a check. All right, so then let's just fill out this expression, put it right here. And we see that gives us 4.5 meters per second, which is not equal to 6 meters per second. So you might be thinking, wait a minute, how can the average velocity not be equal to the initial velocity plus the final velocity quantity divided by 2? Is physics breaking math? No, physics is not breaking math. This expression is the expression for calculating the arithmetic mean of two numbers, actually the unweighted arithmetic mean of two numbers. If you have two numbers, you want to calculate their arithmetic mean, add them up, then divide the sum by 2. The problem is we don't just have two velocities. The velocity starts out at 9 meters per second. It ends at 0 meters per second. But we have an infinite number of velocities in between, right? Because we have velocity as a function of time, and we can put any time in between t equals 0 and t equals 3 seconds. There's an infinite number of times in between, therefore an infinite number of velocities. So we don't just have two velocities that we're taking the average of. All right, so if you want to be safe, taking the average velocity, you need to use the definition of the average velocity. That being said, it turns out that in the special case of constant acceleration, that this expression can be used to calculate the average velocity. We don't have constant acceleration here. That can be seen right here from this expression. Plug in different times, you get different accelerations, so the acceleration is not constant. And so this shortcut will not apply here. So let's interpret the signs. Let's imagine that the positive x direction is to the north. And just so I can use my hands, I'm going to assume that north is this way, up toward the top of the writing surface. So if north is the positive x direction, let's look at our displacement. 18 meters. That's positive, so that means we had a northward displacement in this 3-second time interval. So starting from some initial location, the object went 18 meters to the north. Great. That means the average velocity was also to the north, because that's just the displacement divided by the elapsed time. And so the average velocity was 6 meters per second to the north. That means the object traveled in those 3 seconds the same displacement as it would have if the velocity had always been 6 meters per second. It wasn't, but it covers that same displacement. That's what it means to have an average velocity. Okay, so let's look at the velocity and acceleration functions. At time 0, the velocity is positive 9 meters per second. And then with increasing time, we subtract off ever larger amounts. Until at t equals 3 seconds, we're subtracting off 9 meters per second. So the velocity starts out north at 9 meters per second, and it continues to be to the north until t equals 3 seconds. So it's northward, but then less and less northward. So it's traveling to the north, but slowing down. The acceleration, meanwhile, for any time greater than 0, is always negative. And that's consistent with what I just said about the velocity. This negative acceleration is to the south, while this velocity is always to the north. So if the velocity is to the north, but the acceleration, which is the change in velocity, is to the south, the object will be slowing down. All right, so anytime you have a velocity in one direction and an acceleration in the other direction, opposite that, the object will be slowing down. Just to carry this discussion a little further, let's imagine that this expression doesn't stop being valid at t equals 3 seconds, but continues to be valid for a long time. Let's then continue this discussion about directions. At t equals 3 seconds, the velocity is 0. So v sub x, the velocity will become negative for times after 3 seconds. Well, if north was the positive x direction, then a negative velocity would mean a velocity to the south. So that means after the thing has come to rest, like the thing comes to rest at the instant of t equals 3 seconds, and then after that, the velocity is toward the south. So the thing will start moving to the south. And notice, we'll have an ever greater negative velocity as this time gets greater. So the thing will be traveling to the south, and it'll be going faster and faster to the south. Well, look at the acceleration. The acceleration is still negative, which means the acceleration is to the south. So it was to the south before, and it continues to be to the south. So now we have a velocity to the south, an acceleration to the south. That's consistent with the thing going to the south and speeding up to the south. So if the velocity and acceleration are in the same direction, the object will be speeding up. At the risk of possibly causing confusion, I would like to discuss the term deceleration. Deceleration does not mean negative acceleration. Deceleration means, in the context of one-dimensional motion, object slowing down. All right, so let's look at the full range of motion, not just up to 3 seconds, but after t equals 3 seconds when we extended the range of validity of this expression. For the duration of the problem we've discussed, the acceleration was negative. However, up to t equals 3 seconds, from t equals 0 to t equals 3 seconds, the object was slowing down. That's where we had deceleration. But beyond t equals 3 seconds, the object was traveling to the south and speeding up. It was not decelerating. Speeding up is not decelerating. The term acceleration can be positive or negative in the context of one-dimensional motion. It's a general term. Deceleration is very specific and means object slowing down. You need to be very careful about that term. All right, I hope this example was helpful. That's all I've got for now. Thanks for watching.